In our previous videos, we were talking about this notion of taking two kind of arbitrary vectors in the plane. So let's say that we had a vector v and we had a vector w. And under what circumstances could we take those two vectors and then be able to represent any other vector in the plane in terms of v and w? So that basically we would be able to write u as being some linear combination alpha times v plus beta times w. And the fact that we took away from that discussion was that if v and w were not parallel, then this was all that we really needed to be able to use them to represent any other vector in the plane. And so our question then becomes, how do we generalize this to higher dimensions? And so what we need to do probably first is to kind of formalize this notion of a linear combination. So let's start off with a definition of that. A linear combination of a set of vectors say v1, v2, all the way up to vn of those is an expression of the form alpha 1 v1 plus alpha 2 v2 plus dot 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 all the way up to alpha n vn for the alpha i's being just real numbers. And so when we talk about linear combinations, that's all that we're doing. We're taking a collection of vectors, we're scaling them, and then we're just adding them together. So this actually brings up a question. If we had a collection of vectors, say v1, v2, all the way up to v sub k, where let's just assume that none of those vectors are going to be the zero vector, so I up to 1 to k, and if we had two linear combinations of those vectors, so alpha 1 v1 plus dot 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 all the way up to alpha k v sub k, and then we had another representation, beta 1 v1 all the way up to beta sub k v sub k. Under what circumstances will those two representations yield the same vector? So if the representations were not unique, so if these actually ended up being the same vector, so if we had that alpha I was not equal to beta sub I for some I, then what can happen is that we can reorder things, put groups 1, our I term on one side, and we could group all of the other terms on the other side. So we would have j going from 1 up to k, where j is not I, because we moved I to that side. And we just have beta sub j minus alpha sub j times v sub j. So we could isolate our v sub I term, and then because that coefficient is not 0, we can actually divide by that term. And so what we have is that v sub I looks like just our sum. J goes from 1 up to k, where j is not I, of beta sub j minus alpha sub j over alpha sub I minus beta sub I times v sub j. And so what we're able to do, if those representations are not unique, we can take one of those vectors and actually represent it in terms of a smaller set. So we can represent one of our vectors in terms of the others. So basically, when we have this set of vectors, v1, all the way up to v sub k, if the representations afforded by the linear combinations of those are not unique, then we can, in essence, kind of throw out or remove vectors that can be represented in terms of the remaining vectors. And so in this way, we can kind of take our set of vectors and whittle them down into what would be like a minimal set of vectors. So we want kind of a minimal set of vectors that can give unique representations. And this is actually our concept of linear independence. And so with that, we can make a definition. A set of vectors, non-zero, say v1, v2, all the way up to v sub k, are linearly independent if and only if we have a linear combination. So if and only if for any linear combination, say alpha 1 v1 plus alpha 2 v2 all the way up to alpha sub k v sub k, a linear combination that gives us the zero vector, then the only way that can happen is for alpha 1 to be equal to alpha 2 all the way up to alpha sub k being 0. So the only way that we're actually going to get the zero vector is for all of our coefficients to be 0 in the first place. And this will ensure that our representations by our linear combinations are going to give us unique vectors. So some other terminology that kind of comes along with this. Let's make another definition. So if we're given a set of vectors, say v, and that set of vectors is v1, v2, all the way up to v sub k, then we can define something called the span of the set of vectors. And the span of that set of vectors is really just the set of all possible linear combinations. So the sum from I goes from 1 to k of alpha sub I v sub I for alpha sub I just being a real number for I going from 1 up to k. And so kind of the set of all possible linear combinations is really what we mean by the span of a set of vectors. And so what we have is that a set of vectors are going to be linearly independent exactly when the representations in the span are unique. Are unique. And so this gives rise to yet another definition that we'll make as far as a basis. So a basis is a set of vectors in, say, our vector space R to the n, such that any vector in R to the n can be represented uniquely as a linear combination of vectors in the basis. And so basically what this means is that if we've got a set of vectors, say v1 up to v sub n, then this set is a basis if and only if B is linearly independent and the span of B is our entire vector space. So now let's continue with the following lemma. Suppose we have a set A, and that set A consists of a set of n vectors, so v1, v2, all the way up to v sub n, with A being linearly independent. Now let's suppose that we had a vector w, and the vector w looked like alpha 1 v1 plus alpha 2 v2 all the way up to alpha sub n v sub n. And let's further suppose that alpha sub I was not 0. Then for a new set, for the set A prime equal to v1, v2, all the way up to v sub I minus 1, and then we replace v sub I with w and keep everybody else the same. Then A prime is also linearly independent, and furthermore we don't change the span, so the span of A is going to be the same as the span of A prime. Now let's see if we can prove this lemma. So the proof. Well, since A sub I was not 0, then we can actually write v sub I as being 1 over alpha sub I times w minus the sum over all of the other vectors, where j is not equal to I, of alpha sub j over alpha sub I times v sub j. So we can express v sub I in terms of the other v sub j's and w itself. If we then have any old linear combination, so let's say that we had beta sub 1 v sub 1 plus all the way up to beta sub I minus 1 v sub I minus 1 plus beta sub I times w now plus beta sub I plus 1 times v sub I plus 1 all the way up to beta sub n v sub n, and that was equal to 0. Then what we can do is to replace our w with our expression in terms of the v's. So we have something that looks like b1 v1 plus all the way up to beta sub I minus 1 v sub I minus 1 plus beta sub I times the sum, j goes from 1 to n, of our alpha sub j v sub j plus our beta sub I plus 1 v sub I plus 1 plus all the way up to our beta sub n v sub n, and that's still equal to 0. Well, now we can just do some rearranging and group our terms together. And so what this gives us then is an expression where we have a sum where j is not equal to I, so we can group all of the terms that are not equal to I together. Then that's going to give us something that looks like beta sub j minus our beta sub I times alpha sub j times v sub j from our sum involving our w plus, and then the only term that we have left over is our v sub I. So we've got our beta sub I and then our alpha sub I times v sub I. And this still gives us a linear combination of the v's that equals 0. But because we said our v sub i's were going to be linearly independent, what that tells us is that each of our coefficients in that sum must be 0. So in particular, we have our beta sub j minus beta sub I times alpha sub j equal to 0 for j not equal to I. And then for our I term, we had beta sub I, alpha sub I equal to 0. But we assumed that alpha sub I was not 0. Okay, that's how we chose I to begin with. And so the only thing that we're left with there is that beta sub I must be 0. Well, this in turn means that beta sub minus 0 times alpha sub j was going to be 0. And so we have that beta sub j was 0 for our j's not equal to I. And so what we end up with is that all of our betas were going to be 0. And that's exactly what we needed for our A prime to be this set v1, v2, all the way up to v sub I minus 1. Replace v sub I with w, and then continue with everybody else. That this set is linearly independent. And finally, since we had w being our sum of the alpha j's, v sub j's, then what that tells us is that our span of A prime is going to be contained in our span of A. So we can take any vector expressed in terms of the v sub j's and w and write them in terms of just the v sub j's, including the v sub I. Likewise, since we had v sub I as 1 over alpha sub I w minus our sum of j not equal to I of our alpha sub j over alpha sub I v sub j, that tells us that our span of A is going to be contained in our span of A prime. Thus, our two spans have to be equal. And that tells us that in the end, if we have a vector that's a linear combination of other vectors, we can pick out a non-zero coefficient in there and replace the original vector with this linear combination of the other vectors and still not lose our linear independence. That's going to come in handy in the next theorem, and will have an important bearing on our notion of dimension. Now let's suppose that we had another lemma. And in this lemma, if we have a set of vectors, v1, v2, all the way up to v sub n, and we had another set of vectors, so let's say we had another set of vectors b, let's call those w, so w1, w2, and we've got a total of w sub m of those, with both A and B linearly independent. Also, let's assume that B is going to be contained in the span of our set A. Then our conclusion is that M has to be less than or equal to N. And let's see how that works. So starting off with our proof, since our very first W is in the span of A, then it means that W is going to look like, W sub 1 is going to look like our sum alpha I v sub I for I going from 1 up to n. Now, since our set B is going to be linearly independent, it means that this W sub 1 is not going to be the zero vector. And so there's going to be some coefficient in our V's that is not going to be 0. And so with that, we can assume without loss of generality that that coefficient that's not 0 is going to be alpha 1. So what this means by our previous lemma is that we can replace V sub 1 with our W sub 1, not change our span, and still maintain linearly independence. So our set A1, where we replace W1, or replace V1 with W1, and keep everybody else the same, is also going to be linearly independent, and the two spans remain the same. So the span of A1 is going to be equal to our span of A. So for our vector W2, that thing is going to be in our span of A1, which was equal to our span of A. And so we can write our W2 as being alpha 1, 2 times W sub 1 plus our sum now, j goes from 2 up to n, of our alpha j sub 2 times v sub j. Now, again, one of these vectors, since W sub 2 is not 0, one of these coefficients is going to be non-zero. And if alpha 2j was going to be equal to 0 for j being 2 up to n, then basically what we have is that W2 is going to be equal to alpha 21 W1, and so those two vectors W1 and W2 are not linearly independent. And that would give us a contradiction. So what we must have is that alpha sub 2j is non-zero for some j with j greater than or equal to 2. And so, without loss of generality again, we can assume that this is for j equal to 2. And so, what we can do, again, by our previous lemma, now we can come up with a new set, A2, where we just replace v sub 2 with w sub 2, and we keep all of our other v's. Now you can probably get an idea of where this is going, that we just kind of keep the same argument, wash, rinse, and repeat, for W3, W4, W5, all the way up to as far as we can possibly go. So we can just repeat this process a maximum of n times. As soon as we would try to do something like w sub n plus 1 being in the span of our set w1 dot 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 all the way up to w sub n, now we lose our linear independence. And so what that tells us is that our process has to stop either at n or before n. And so we have our conclusion that our number of vectors m has to be less than or equal to n. And so this brings us to kind of one of our main theorems, and that being that if we had two bases, so b being v1 up to vn, and b prime being a set w sub 1 up to w sub m, and these are two bases for our vector space r to the p, then our conclusion is that n is equal to m is equal to p. So now let's look at the proof for why that might be true. So by the previous lemma that we just had, that b prime is going to be a linearly independent set in the span of b, and so that tells us that m has to be less than or equal to n. But also, b is a linearly independent set in the span of b prime. And so we also have that n is going to be less than or equal to m. Since r to the p is spanned by our standard basis, so our E1, E2, all the way up to E sub p that we talked about before, then we have to conclude that n has to be equal to m, and that also has to be equal to p. And so kind of the punchline being, if we've got any two bases for our vector space, that those two bases are going to be the same size. And so our notion of dimension is going to be a well-defined concept. And so we can conclude with the following definition. The dimension of the vector space r to the d is the cardinality of any basis for r to the d and is equal to d itself. And so our maximum number of vectors that we can have in any subset that are going to be linearly independent has to be of dimension d. Anything beyond that kind of forces them to be linearly dependent. And so now that we've got this notion of linearly independent vectors defined and this notion of basis defined, now we can start to look at a couple of operations on our vector spaces and see what other kind of information we can get from those operations.